on behalf of all of us for getting us together. This is great. We've had some beautiful talks today, and yes, I'm going to take it back to a bit of an old school kind of talk this up now. And I should, before I start, I should say, I feel like a bit of a fraud giving this talk. I actually think Sylvia or Rob should be doing it. So this project grew out of a discussion. Rob sort of said, you know, we really should go back and look at serotonin in axon guidance. In the early days of the axon guidance field, serotonin was a really common cue that people used to study axon outgrowth in vitro in particular. But then in the 90s, when the netrons and robos and slits and nephrons were discovered, serotonin kind of fell by the wayside in terms of the axon guidance field. And so Rob and I sort of had a discussion about it, and, you know, there's quite a bit of conflicting, or what appeared at the time to be conflicting data in the literature. And so we thought it would be a good topic to revisit. And Silvia Vicenzi, very talented PhD student, arrived in our lab from Italy via Sweden, an adventurous young woman who's done some beautiful work. And so this is really her work that we're going to talk about today. And we've just published this in Cell and Molecular Life Sciences. Just came out last week. So yeah, we'll see how we go. Okay, so we all know about serotonin, and we all know that it's so important in all aspects of neuronal function. So, you know, in the adult brain, we know it's important for cognition, for sleep, arousal, behaviour, motor function, etc. And in development, we know it's really important in migration and in proliferation, synaptogenesis. And as I mentioned, enhancing and inhibiting axon outgrowth has been seen previously. It's implicated in pretty much all nervous system disorders that we know about, as obviously depression, and schizophrenia and autism and so on. And so we wanted to look a bit more closely at serotonin in axon pathfinding, and whether it not only influenced neurite outgrowth, but neurite navigation and turning. And one of the reasons that we think it's likely plays an important role is serotonin's like one of the first neurotransmitters that's out there. And it's one of the serotonergic neurons are some of the earliest that are out in the brain. We know there is data to show that it does interact with other axon guidance cues. So, for example, activation of the 5-HT2A receptor can abolish ephrin-mediated turning of thalamic axons across the midline. Similarly, the 5-HT1B receptor, if you activate that and these zebrafish studies, for both of these, you can actually cause switching of axonal responses to netrin from attraction to repulsion. So clearly there's data to show that serotonin can modulate the effect of other axon guidance cues. But we wanted to know, could serotonin actually play an instructive role in axon navigation in its own right? Is it a bona fide axon guidance cue as well, given that it's out there so early in that developing nervous system? I'll talk about the receptors a bit more in a minute. So for those of you that haven't seen our work, we have a long-standing, we've used the Mu-Ming-Pu growth cone turning assay for a very long time now, where we have dorsal root sensory neurons, embryonic rat neurons growing in a dish dissociated. We have a pipette puffing a guidance cue about 80 microns away at a 45-degree angle. And we simply measure the trajectory of the distal axon at 30 minutes. So we compare its angle at 0 to 30 minutes and look at whether we get a positive or attractive turning angle towards the pipette or a negative repulsive turning angle away. It's a very simple quantitative assay. So the first experiment Sylvia did was simply a dose response curve to look at this turning. And so she compared serotonin turning to the gold standard, so to vehicle, just to vehicle in where we get random turning, so not attractive or repulsive. Gold standard attractive cue in this assay is BDNF, and semaphore and 3A a repulsive, classical repulsive cue in this assay. And she looked at a range of doses ranging from 0.5 micromolar out to 100 micromolar of 5-HT. And what you can see is that you can see as she gradually increased the dose, she got to a quite robust attractive response at 50 micromolar. That's quite, it's indistinguishable from the BDNF response. So classic attractive response at 50 micromolar. But then as she increased the dose, at 75 micromolar, we went back to random. And then at 100 micromolar, it was a repulsive response, not indistinguishable from SEMA3A, so the same as SEMA. So we had this biphasic response of serotonin attraction at 50 micromolar, which we now, for the rest of the talk, we'll talk about. On the graphs, it'll be labelled as 5-HT low, which is the 50 micromolar attraction, and 5-HT high, 100 micromolar. So with serotonin, the receptor landscape is complex. There are 14 different, at least 14 different serotonin receptors, 7 different classes. All of them are G protein coupled receptors, except for 5-HT3, which is an ion channel. And many of them are expressed in dorsal root ganglia, but the two that are most abundant, and this has been described since the 70s in the literature using biochemical assays and so on, 5-HT2A and 5-HT1B are the two most abundant receptors in the DRG. So Sylvia did some immuno to look at those on the growth cone, and you can see that there's quite a lot of receptor out there, 5-HT1B and 2A, and there's quite a bit of co-localization, which you can see over on this filopodia here. So, yep, the receptors are there as we would have expected. So which receptors are responsible for the attraction and repulsion? So looking at the 5-HT2A first, it's a G-alpha-Q coupled, G protein coupled receptor. So it activates phospholipase C signaling, which apart from diacylglycerol also activates a calcium, an IP3 mediated calcium influx out of the ER. So that's a fairly simple testable hypothesis using pharmacology, which Sylvia did. So there's a lot on this graph, but it's not too difficult. So as you can see with vehicle, we get random growth. With the 5-HT low, we get the attraction. And then if we use a specific agonist of 5-HT2A, the TCB2, which is a highly potent selective agonist for 2A, again, you get that attractive response. If you use ritanserin in conjunction with the 5-HT low, so Bath applying ritanserin, that's a specific antagonist of the 2A, and you can see that we block that quite clearly. And also if she blocks phospholipase C with a specific inhibitor, you also block that turning. So nice data to demonstrate that the 2A does indeed mediate growth cone attraction towards serotonin. These are, over here we had experiments where she tried to block the 5-HT1B, which had no effect on growth cone attraction. She used ondansetron, which is an inhibitor of that HT3, the ion channel receptor for serotonin, and no effect on there. We looked at whether calcium influx was coming across the membrane via L-type voltage-gated channels, and so blocking those had no effect. But if you depleted calcium from the stores, so if you depleted calcium from the ER with Bath application of thapsigargan, you depleted the attractive, or abolished the attractive response. And so that confirmed that this calcium-mediated, IP3-mediated calcium rise was necessary for that serotonin-induced attraction. And we can see that calcium response here. So she did some nice calcium imaging to go along with this. So you can see that with 5-HT low applied here, and there's a gradually slow increase of calcium in the growth cone, which you can see up here. It's quite a slow response, and that's typical of the GPCRs, so much slower. GPCRs are known to act within minutes compared to the seconds of the ion channels. And you can see that 5-HT high, the repulsive concentration had no effect, didn't cause a calcium signal at all. So that all seems really nice data to demonstrate that the 2A receptor for serotonin mediates growth cone attraction towards serotonin. So what about this repulsive? Which receptor is that? So again, we thought it would be the 1B. It seemed the most logical candidate. It's, as we said, it's very abundant in DRGs, and it's a G-alpha I, so it's an inhibitory G protein coupled receptor. So it inhibits adenylate cyclase activation of cyclic AMP. So normally we associate cyclic AMP activation with, if it's activated, it's usually associated with growth cone attraction. If it's inhibited, it's often associated with repulsion. And so it seemed like a good candidate to mediate growth cone repulsion. So this is the pharmacology for that. So here is the vehicle again, and the high concentration of serotonin. If you put in a selective agonist of the G-alpha I, you get, again, you get that growth cone repulsion. If you block it with a specific antagonist of the G-alpha I, or the 1B rather, the H1B, you block that repulsion. And then, interestingly, if you bypass the receptor and activate cyclic AMP signaling, either with forskolin or cyclic SP camps, which is a cell permeable activator, you can also block repulsion and actually almost trend towards attraction, but not quite. So again, over here are all the controls where Sylvia tried ritanserin, which is the inhibitor of the 2A receptor. It had no effect on the repulsion. Similarly, on ondansetron, the inhibitor of the serotonin type 3 receptor, no effect. Depleting stores with thapsigargan or blocking L-type calcium channels also had no effect. So consistent with the no role of calcium signaling in this turning. So then Sylvia did some nice work using something we've been wanting to do for a long time, and there's some nice tools now to actually look at cyclic AMP in the growth cone. And so she used the Flamingo 2, which we got from Adgene, and it worked really well in the growth cones. You have to get your head around it, because the fluorescence, as the cyclic AMP signal increases, the fluorescence decreases. So this is shown up here, where fluorescence goes down in response to forskolin activation of cyclic AMP. And so if we look at what happens when we puff either 5-HT low or high, we'll start with high, as we would expect, because the activation of the 1B receptor inhibits cyclic AMP signaling, we should see an increase in fluorescence, which we did. Conversely, the 5-HT low, which we know, we saw from Sylvia's work, activates a calcium signal, which we know often then activates cyclic AMP signaling. We see an increase in cyclic AMP activity, which in this case looks like a decrease in fluorescence, and that's just quantified here. So really nice demonstration of the two receptors, the 5-HT2A mediating attraction to serotonin, and the 5-HT1B mediating repulsion. Sylvia also did quite a lot of work looking at receptor localization in this turning, and I'm just going to show you a little bit of it. But in response to 5-HT low, you could see that the 2A receptor was trafficked to the near side of the, over here, near side of the growth cone, closest to the pipette, so close to the source. So the 2A receptor would be trafficked out to the periphery of the growth cone, whereas the 1B receptor didn't appear to be trafficked in the same manner. So that suggests that in response to growth cones growing towards the 2A, the 2A receptors getting prioritised out on the periphery. One last experiment, we often collaborate with John Lynn's lab, and John's PhD student, Jade Lockyer, another very talented Tasmanian PhD student, is developing a tool to manipulate GPCR signaling. So she had developed a tool that actually inhibits the G-alpha-Q, so 5-HT2A, in this case, for serotonin signaling. And so we wanted to use her optogenetic tool to see if we could, if it inhibits G-alpha-Q, in theory, we should be able to transfect the neurons with this optogenetic tool, shine blue light, and inhibit turning towards that low concentration of serotonin. So that's what Sylvia did, and there are a number of controls here. So first of all, just expressing the tool on its own or a light insensitive version of it, and then looking to see whether the growth cone, if you shone blue light on them, did they turn on their own, and they didn't. So these are inhibitors of G-alpha-Q, so there was no background activity per se in terms of turning. So I should say we have a setup where we can illuminate one side of the growth cone to get the growth cone to turn. We've done this before with other optogenetic tools, and so we wanted to see if we could get the GPCRs to make the growth cones turn. So on their own, no, they didn't turn. This is just the attractive concentration of serotonin in combination with blue light, just to make sure the blue light didn't affect that normal attractive response, and it didn't. The growth cone still turned towards low concentration of serotonin. But if you now activate the optogenetic tool to inhibit G-alpha-Q in the presence of low serotonin concentration, we actually, Sylvia actually inhibited that attractive turning. The light insensitive version had no effect. We still got attractive turning. And similarly, if you put the tool in but didn't have blue light, you didn't affect turning either. So this showed that the G-alpha-Q tool was actually acting quite specifically in terms of inhibiting serotonin-mediated turning. So that was really nice. So that's just a short story of how we think serotonin's working. And so how we think it's working mechanistically is that serotonin can mediate chemoattraction via 5-HT2A and chemorepulsion via 5-HT1B. And we think what's happening is that there's data to show that G-alpha subunits can inhibit microtubule polymerization, while the G-beta and gamma subunits can promote microtubule assembly. So what we think is happening is when the 5-HT2A receptor is being activated by serotonin, you've got the G-alpha-Q activating the calcium signaling via the IP3 pathway. And then we think that the G-beta gamma is promoting microtubule assembly, and so you're getting attractive turning towards the serotonin. However, we do know, and there's a lot of biochemical data in the literature to demonstrate this, that the 5-HT2A receptor gets desensitized over a time and concentration dependent manner. It gets internalized by a clathrin mechanism. And so our hypothesis is that when we go up to that higher concentration of serotonin, you're desensitizing the 2A receptor, and so the 1B receptor gets activated. So it seems like there's this preferential activation of 2A, and given that 2A is trafficked to the near side of the growth cone in response to low concentrations of serotonin, you can see that growth cones can you can see its mechanism where basically serotonin's acting as a start-stop signal, where growth cones detect that serotonin, grow towards it, and receptors get trafficked out there and the microtubules go that way. But then as it gets closer and gets closer to this high concentration, you get a desensitization, and so the 2As get internalized, and so the 1Bs are activated instead, and then you get repulsion and stopping. And so it's, I think, a nice part of the serotonin story to illustrate how serotonin can help set up the early circuitry of the nervous system. And so with that, I'll just say, as I said, Sylvia did a great amount of work on this project with the help and guidance of Rob in the lab. And thanks to Jade and John for the optogenetic constructs. It's a nice little tweak. And I should say Jade and Sylvia are now working on doing some lovely experiments of guiding axons in vivo with those constructs. So that's in the fish and the worms. So that's really good fun. Okay, thank you. And thanks to funding and to all of you for listening.
Thank you very much.
Thank you very much.
Fantastic.
Okay.
Thank you, Lisa. That was really short and sharp and really opens lots of questions from a very targeted experiment. So thank you very much for your presentation. Lisa, I will now open the floor to questions, and I noticed that Massimo has anticipated all of us and has his first question to ask. Massimo, can I please ask you to address Lisa with your question? Thank you.
Lisa, can you hear me?
Yep, I can hear you, Massimo.
Beautiful talk.
Thank you.
I was wondering if you show the asymmetric distribution on the growth cone on the 5HT2A. Do you see also the 5HT1B, the asymmetric localization, or on the other side?
Yeah, so Sylvia did a lot of work on this with permeabilizing and non-permeabilizing of the cells. And so if you, in the permeabilized situation, you see the 5HT1B move, but we think, so that would suggest that there's a pool of receptors inside the growth cone moving, but when you look at the non-permeabilized, so look at just the membrane expression, it's mainly the 2A that we see out there.
Okay.
So we think there's so much receptor there anyway. What's confusing is why the 2A gets, so the 2A does get preferentially moved out there. So I guess, and we know from Jeff's modeling work that that doesn't take much receptor to get activated to get that asymmetric turning. So I guess that's, we hypothesize that that's why the 2A gets activated first.
So if I can ask a following up question,
Sure.
Okay. So when you have the calcium, when you look at the calcium transients, with the low calcium, you see with the low serotonin, you see the calcium activity inside the growth cone. What it's really interesting is that when you have high concentration, you seem to not see that. So is the hypothesis that the activation of the 1B is blocking the calcium, because in principle that receptor should still be activated?
Yeah, it's interesting, isn't it? You'd think that you would get the 2A activated as well, but what we think is happening is when you get that high concentration, you've desensitized the 2A, and it gets in. There is biochemical data to show, and previous data that shows that it gets internalized. And so you're probably not activating as much 2A. So the overwhelming response you see is the 1B.
Okay.
Which is the flat line. I was surprised that it was so flat, that the calcium was so flat, but yeah.
Yeah, thank you.
Thank you, Lisa. Helen also had a question, and because it's a question, yes, short and sweet, but Helen, I pass the floor to you.
Okay, thanks. Interesting talk, Lisa. I'm just wondering, I guess I'm wondering more about central nervous system rather than peripheral, but either way, is there any knockout mice, and is there a hint that how this actually works in vivo?
So there are knockout mice, and there are guidance defects in these, and I'm just blanking on which tracks they are at the moment, but there are definitely connectivity defects in the knockouts, and these have been looked at in the past, but not really looked at in terms of guidance, not examined with a guidance lens on it. So it'll be worth going back and having a look at those in more detail. So that's something we'd like to move to. So we haven't done any of that, but that's been done previously. And the connectivity defects have been described.
Okay, good.
Thank you, Helen, for your question. Do we have any other pressing questions for Lisa and her presentation? Please do not be too concerned if you are formulating a question now. You can always send it through to Lisa directly, or we are happy for you to send us questions to Lisa, which we will convey. But really, that's the message of this forum. we are all amongst friends and colleagues, and we are encouraging everyone to contribute to the conversation. And I understand for all of us that Zoom is not always the most personable approach, but it has brought us all together today from all over the world. And it's been really fantastic to see cell biological systems as well as animal models and comparative neurobiology applied in the presentations from 3 different organisms. And so that's a wonderful tie-in here from all the presentations today. So Lisa, thank you very much for your presentation, and thanks everyone for your presentations today. Can I just take this opportunity to ask Kelly and Natalie and Mike to to put themselves on video, and for us just to say and to give everyone a wave to all us brave pioneers that have arrived at this Zoom call today to be a part of the inaugural ADNF meeting. And it's really dispersed leadership here, folks. Natalie and Kelly and Michael and I have really been a real pleasure to have, for me, to have worked together to bring the program together, and for everyone to have contributed today, as well as the program following. So on behalf of the 4 of us, I just want to say thank you very much to everyone to attend, as well as to ask questions. So Mike is hosting these sessions through the Queensland University of Queensland's Zoom chat platform, and so we really appreciate the use of UQ's resources for this. We will post a video recording of this session in due course, and I just want to take this opportunity for all of us here at ADNF to remind you all, please register and encourage your friends and colleagues to register to receive updates on the year-long program. We are excited to forecast that we have speakers through till February, and these hail from France, New Zealand, Taiwan, the US, the UK, and of course Australia. And we will update you with this program in due course through our channels, as well as through Natalie's very swift social media handling of our promotions, and she is really indispensable to the programming as well. We are going to be featuring work on Drosophila, mammals, organoid work, single cell genomics as well. So the program is vast. We would encourage everyone at every level to consider participating in this conversation, this ADNF conversation. We would love to hear from you. And in addition to the 20-minute presentations that we have that we are going to program for this symposium series, we'd also love to hear from the ECRs and the PhD students through formats that are specifically designed for you and the audience to be able to show and tell. This is really something that we will feature in the near future, and also that we are looking for everyone to provide us with some feedback as to how we can continue to improve, and for the old folks to tell the early and earlier career researchers how we got here. That's another idea that we are thinking to develop, because all we can do is to help each other, and none more so than in this forum. I see, and we see the ADNF to be able to do this in a very personal way. So Mike and Natalie and Kelly, I will now hand over the floor to you for your closing comments, if I may. Thank you.
Thank you, Julian. I've been amazed by the quality of the talks today. It has been a real pleasure to listen to all of you. Thank you, guys. And really looking forward to having you for the next talks, next seminars. So we opened the Twitter account recently. I will just put on the chat the Twitter handle if you can follow us, and to have the news also on the ANS Twitter account and Facebook page. Please follow us, and see you in October then.
Yep, lovely folks. It was a pleasure. Thank you to all the speakers. Kelly, did you have anything to say? Just thanks, everyone. It's been great.
Perfect. Okay, well, enjoy your Thursday, folks. I'll close off the meeting and take care. Cheerio.
Bye.